You just multiply the element of the ring times whatever this guy is doing on the module element. Plus delta, which is given to you because it's here, applied to the ring element times the modulo.
Okay, so what does nabla delta do on the module element?
Whatever it wants. It's a mapping.
Right. So
It's a mapping. Let me emphasize. There's a huge space of these connections. It's a mapping. I mean, it's some mapping. It's your friendly mapping, a mapping you hate, or whatever. Okay? This thing is called a connection. And we go to this full space script C of all connections of this type. Of course, fixing the ring and the module. Yes.
Are the differential operators on the module vector space?
Oh, yes.
And is
That's a very important remark. Did you hear? I'll repeat what you just asked, and I know what's going to happen coming up. The space of differential operators, I told you what it is. It just has to behave like this, a differential operator. And it's completely clear if you multiply that by something in the ring, it's still a differential operator, right? So, yes, the space of all these differential operators of first order is also a module. And so, and this is our modulemorphism. Yeah? You understand what that means? That means that nabla of f times x is equal to f times nabla of x.
so basically a connection is vector space morphism, which has this additional row.
That's right. It's our modulemorphism.
And
That's it.
Is the space of connections also vector?
We talked about that last time. I'll say it again. No. It's an affine space. So, in order to understand that space, fix a connection, and any other connection differs from this by a translation so that you can just think of it as an affine space. So the space of all connections is not so bad. I mean, okay. And by the way, you can see it's a lot better than the space of all metrics. Yeah, a metric is a very strange thing, right? But this a big help of this is Levi-Chivi to this contribution. The space is, these things are very simple things. It's just the definition looks so. Okay. Now we have a few minutes. Are we okay on that? I think we're okay on that. So our context in geometry, in differential geometry, our context in the smooth setting is, I'm just repeating everything I just said, the ring, it's really a Schiefer ring, so but anyway, for any open set, but I'll formulate it for the full manifold M, and that's the ring, and the module is the space of C infinity sections of a vector bundle over the base. Okay. And I think almost exclusively at the beginning of physics, the vector bundle is the tangent bundle. Okay. Or the cotangent bundle. Or tensor products of this. In our notation, I'll say it again, is X, which is a vector field on the manifold. That's derivations on this ring. It's mapped to nabla of X, and nabla of X times times the section. It's just f times nabla of the section plus x of the vector of the function times. It is an extremely deep concept. It looks trivial to you, I know, but it somehow is extremely deep. Riemann had it in his mind, but it took a long, long time to formalize it correctly. I think Levi-Civita could not have said this. I think it was a long, long time until we could really say it. Okay. Now, notation. For n, for t and the tangent bundle, for E for the tangent bundle. In a frame. So i.e. what we're talking about the tangent bundle over a coordinate chart where u has a frame, where t of u has the frame, usual frame of coordinates d1 to dn. Okay? Okay? So if we have a frame, we have a chance of writing this down. This is what we talked about yesterday, and I want to talk about it again. Okay? In the frame. Okay. Now let's recall what goes on. So what goes on is this, is a section, is the sum of elements fi di. Okay. It's the sum of this in this picture. This is a local section. This is an element. This is in this frame. This is how you write a section in this frame. Okay, that's good. Now you have a vector field x, a vector field, say on wherever this thing is defined. So x, a vector field on U. You want to differentiate these things because we're given this connection, fi di. Well, the rule told you how to do it. It's fi nabla of x delta I plus nabla x f. Wow, nabla x of f, we know, that's given to us. X of f di. This part here is standard. This part here is non-standard. This is given to us. So physics or somebody who's studying geometry, this gives it given. So we need to compute. We need to write that down if we're going to do calculations. We need to do this. Right? We need to do that. Well, x, we have a big break here. X itself is a vector field. So, you know what I'm going to do? You're going to hate me for this because I think I'm going to change indices on you, and this is going to happen throughout the semester because I am terrible. I think I want to change this I to a J. So be patient, please. Okay. X, I think, so I'm going to write it x down with I. So x is a vector field. X is a vector field. C I di. And you can see I'm in big trouble if I'm differentiating di with things in this sum, right? So I'm going to change this thing to dj. Okay. I'm sorry I'm doing this to you. This is terrible. You understand what's going on here. I think I need to call this dj. I hope. And now I'm going to write this guy out. And then I'm going to go to her remark is she says that's just an R modulemorphism. So x goes linearly to whatever combination of the x it's just linear. So this is R modulemorphism. So let me just write this here. Ci di. I change that to j. And so what this thing is, this is Ci d nabla of di dj. it's linear in this argument here. That is the statement that this is an R module mapping. It's linear over the vector fields. Right? Yes.
So whenever I go to this, you're assuming the Einstein summation.
Yes. Yes. Again, I'm not writing the summation here ever. Okay? You just get used to it. This is not a problem. Okay? Well, therefore we need to know this guy. This is the key. Because this part is trivial. We know what that is, just vector fields on functions. This is just linear in this thing. This is linear over the x. So this ci comes out here, so it's just ci here. So this is the key thing we need to know. So nabla of di dj is again a vector field because it's a differential operator on vector fields. What is it? What did I say? You take a vector field and apply it to a vector field. It's a differential operator. So it's you're going to get a vector field. So you're going to get a vector field which is some linear combination of dk. So it's some linear combination of these things, and some people write that as a Christoffel symbol. So some people write this as a Christoffel symbol. Okay? We talked about that yesterday. You're really okay on this now, right? So this guy here, this Christoffel symbols, tells you completely what this connection does because everything else just follows by linearity. Right? Okay? So this thing is Christoffel symbol. Now, I think one of the psychological breakthroughs in this subject is due to Chern. And since that time, we have written this slightly more generally. We have written delta x of dj. And now here I want to be careful. I think I want to follow the notation. I think Chern's number is notation of di is omega of omega ij of x dj. So I may have transposed this matrix, I'm not sure. Okay. Right. So do you see what's happening here? You apply something to x, which gives you these coefficients here. So omega is a matrix of one form. And this matrix of one forms is given to you by the Christoffel symbols. Christoffel tells you how to apply the connection to either di or dj, depending if I make a mistake. Right? And this tells you how it's a matrix of one form to anything. So this is called a connection matrix. Okay. That's it. I won't bother you with any more of this nonsense. That's it. Okay. The next step is Riemannian metrics and associated connections to Riemannian metrics. And so on. Okay, see you this afternoon.